Welcome everyone to our video on balancing redox reactions by oxidation number. In this video, our goal is simply to learn the process of how to balance these redox reactions using the method of oxidation numbers. Going into this video, there's two things that you need to know, despite the fact that there's three arrows there. The first thing is that you need to know how to assign oxidation numbers. So if you haven't watched that video yet, go watch that previous video, learn that method, do some practice, then come back here. Second, I think it's best to know how to balance reactions by half cell first, and then use the method of oxidation numbers. So it's good to go through that process first and then come here for this one. As we did when we were balancing by half cell, let's start off with the rules, and please pause this video at some point and copy down these rules and have them with you as I'm going through examples. You'll see as you're going through these that some of the steps are similar near the end, where we ultimately need to make sure that the electrons lost through oxidation equals the electrons gained through reduction, and we ensure that the atoms and the charges are balanced in the equation. So take a moment, if you haven't already, pause this video. And now let's move on to a few more rules. If we are in an acidic or a basic solution, we follow the first steps 1 to 3 from the previous slide. And then, in order to balance the charges, we are going to use hydrogen ions. If the solution is acidic, if the solution is basic, we'll use hydroxide ions to balance the charges. Because we've now added hydrogens or hydroxides, we'll use waters to balance the hydrogen atoms from the previous step, and then we'll check our answer by checking that the atoms and charges are balanced. So let's go through two examples of this method. Here's the example we're going to be working with. First of all, we will assume that this is an acidic solution, and that's what we should always assume unless we are told otherwise that it's in a basic solution, or if it's not aqueous at all. The principle that we're going to be looking at here is this. If an element from reactants to products undergoes a change in oxidation state, that's indicative that it has either gained or lost electrons. So that substance there is involved in the redox reaction. So we're going to be trying to identify the elements which have undergone a change in oxidation state. Our first step is to assign all of the elements their oxidation states. This is a good place for you to pause the video and try this yourself. Okay, so here are the oxidation states, and I've listed the oxidation states in blue. The orange numbers above those oxidation states were used for me to figure out the sum of all the oxidation states of the molecule to ensure that those have balanced out. So the oxidation states are in blue, and that's important because we are tracking changes in oxidation states. Let's now identify the two half reactions. I see that manganese has gone from +7 to +4, so it's become more negative. That means it's gained electrons. So there's the reduction, and specifically, the manganese has gained 3 electrons. The bromine has gone from 1 minus to +5. So it has lost 6 electrons. So there's my oxidation reaction. If applicable, we'd want to balance the elements that have undergone the oxidation and reduction at this point. But here we have 1 manganese and 1 bromine on each side. Now we're going to make electrons lost equal to electrons gained. So I'm going to multiply only the species that are involved in the reduction by 2, so that we'll have a total of 6 electrons. And I'll leave everything else alone. Since we're working in an acidic solution, we are going to balance the charges by adding hydrogens. I'll write the overall charge of the reactant side and the product side below here in black. The left-hand side has a charge of -3, and the right-hand side has a charge of -1. So to balance them, we need to make the left-hand side more positive. I'm going to add 2 hydrogen ions to the left-hand side, and now we've balanced out the charges on the left side and the right side. Now that I've added hydrogens, I need to balance those out, and I'll do so by adding waters. I'll add 1 water molecule because each water has 2 hydrogens, and that's the number of hydrogens I added on the left-hand side. So we know the charges are balanced. We know the electrons lost are equal to the electrons gained. We know the species involved in the oxidation and reductions are balanced. The one thing that we haven't checked are the oxygens. So we just want to check now to make sure the oxygens have balanced out. On the left-hand side, I have 8 oxygens. On the right-hand side, I have 4 in the manganese dioxide, 3 in the bromate, and then 1 more in the water. So there's a total of 8. So the charges are balanced and the chemical species are balanced. And we've got the electrons lost equal to electrons gained. So the chemical equation is now balanced. Let's do one more example. In our second example here, we will look at a basic solution. So we know that we're going to involve the hydroxide ions to balance this out. Let's start as we did last time by assigning oxidation numbers to each element in the reaction. As in the previous example, my oxidation states are in blue. And now I'm going to identify the changes in oxidation state. So I see that iodine has gone from 0 to -1. So it has gained an electron. So there's my reduction. Before I go any further, though, I want to ensure that I balance this chemical species. So I'm going to add a 2 there. And so the change here is actually 2 electrons because I have 2 iodines and each of them have gone from 0 to -1. So in total, we've gained 2 electrons. The sulfur has gone from -2 to +6, and so it has lost 8 electrons. Now I'm going to make electrons lost equal to electrons gained. And to do so, I need to multiply the iodines by 4. Next up, we're going to balance the charges by adding hydroxides because we are in a basic solution. Let's check on the charges on the left-hand side and the right-hand side. The overall charge on the left-hand side is 2-. The overall charge on the right-hand side is 10-. So we need to add 8 more negative charges to the left-hand side. Each hydroxide has a -1 charge, so we'll add 8 hydroxides. And since we've introduced hydrogen atoms, we need to add oxygens to balance those hydrogens. I added 8 hydrogens, so I'm going to add 4 water molecules to balance the hydrogens. And once again, I'm now going to check to make sure that the oxygens are balanced. On the left-hand side, I have 8 oxygens. On the right-hand side, I have 4 in the persulfate. And now, just like in the previous example, we're going to make sure the oxygens are balanced. We have 8 oxygens on the left-hand side. We have 4 in the sulfate ion, and then 4 more in the water molecule, so 8 in total on the right-hand side. So all of the elements are balanced, and the charges are balanced, and we know that electrons lost equals to electrons gained.